Hello, my name is Maximilian Bandle, and today I will present our work, Database Technology for the Masters, Sub-Operators as First-Class Entities. It is a vision of our ongoing work with Jana Giceva. Database systems are the cornerstone of computing for decades. They store the data and can return results for simple queries, complex analytics, or even graph or machine learning tasks. However, more and more users turn their backs on database systems for flexibility and performance using libraries and systems like Spark or TensorFlow. By doing this, however, they lose the benefits of a database system. This includes the storage layer, transactions, consistency guarantees, and also the optimizer. For example, there's no optimizer in Spark yet, and for graph processing, transactions are just being developed. So even though it is attractive in the beginning not to use a database system, you keep reinventing the wheel and copy the advances and goodies from the database management system over to your stack. To make matters worse, you also want to use accelerators for data processing. Now, when looking at a database system, it mainly uses the CPU. However, over the last decade, accelerators like GPUs or tensor processing hardware are on the rise. And we'd also like to profit here using a database. Specialized libraries are mostly a step further, as some of them are already optimized for different hardware targets and offer a convenient interface to accelerators. However, now this means our data is stored and processed in several places. But what hinders us from having the same ease of use and flexibility inside of a system? We think it's mostly the relational algebra operators which are the bottleneck. When working with a system, we have to narrow everything down to this representation, which is mainly designed to represent SQL-like queries. Thus, it is non-trivial how to express, for example, iterative computations or tensor operators efficiently and adequately without primarily using UDFs, which have different problems. So now that we are at the relational algebra level, the next problem arises. The operators do not easily map to different hardware targets because they are too coarse-grained. It's also non-trivial how to offload certain parts of the computation when having disaggregated resources. So now, to overcome this problem, we proposed sub-operators. They are logical functions that perform basic tasks in a database management system like scanning or scattering the data. They can of course be used to build classical SQL relational algebra operators we all know and like to use in a database context. However, they are also quite fine granular, so we can compute and compose more complex data flow patterns out of them without having to squeeze everything into relational algebra like we had to do before. Furthermore, the level of granularity allows sub-operators to be specialized for heterogeneous hardware easily, and also to offload parts of the data flow to different hardware targets, for example to move compute to where the data sits. This will transform the database system from an executor of relational algebra to an executor of sub-operators. Thus, we can lower both SQL and other data processing tasks to such a layer and execute it using our database system. To make this vision more concrete, we are showing a sample set of sub-operators. This set includes two types of data access operations: random and sequential reads, which are responsible for accessing the data by using a combination of the primitives. Compute offers the possibility to apply a function on each tuple using the map suboperator, and fold combines multiple tuples into one. To support different control flows, we exemplarily have the loop suboperator for iterations inside of a query. Related work like modularis from ETH, low-level operators from our group, Euler from CWI, for example, also propose slightly different sets of composable intermediate representations. Now, to show the potential of our vision, we use a simple hash join example. It is one of the core operators in a relational database, and it combines two tables. Our version here reads the build side using the scan suboperator and then directly using a hash table using the scatter suboperator. Conceptually, scatter has to do a bit more than just writing to the locations. It also needs a method of taking care of collisions. Afterward, we scan the probe side using the scan operator again, and then we probe the hash table using gather for random access we built before, as indicated by the dotted arrow. This setup already implements a typical hash join. However, now we can also plug partitioning into the setup if we know that we could profit from it. This would put a partitioning operator just in between scan and the following operator. Now partitioning is not in the list of our example sub-operators, so this could mean two things. Either we have to define and implement a partitioning operator, or we build it using the sub-operators to get a composed sub-operator named partitioning. We decided doing the latter, and we build a composed operator. Now we can map the different steps necessary for multi-threaded partitioning to the sub-operators here, as shown on the left and also as explained in the paper. And also going for non-standard optimizations is also possible, like adding semi-join reducers. We can just add another access to the build hash table before the partition of the probe site. This reuses the result from the build site to drop tuples early and speed up the computation if the join is selective. All of this shows that even though it's only an example set of suboperators, it is expressive enough to describe and optimize relational algebra operators. Now, having this execution plan, we can also now think about where to perform the computations. We scan and filter directly in the storage layer, where we have a higher bandwidth available. Now, being in a disaggregated resources setup, we now have to move the data from the storage layer to the compute layer. While doing this, smart NICs can partition the data as well. Finally, the compute layer only has to build and probe smaller hash tables, which uses the caches more efficiently. Using the suboperators here gives us a more natural understanding on how to split the data flow so that offloading is possible. But until now, we only looked at SQL-like data flows. But also non-standard data flows are possible. This example shows one iteration of k-means. We first read all the points, look which centroid is closest, group the points by the chosen centroid, and get the centroids for the next iteration. Again, we have to build the aggregate using our suboperators as a combined operator. But we still perform only one iteration and do not know if we have converged. However, we can solve this using the loop suboperator for control flow. Loop looks if the centroids changed since the last iteration in this case, and if not, returns the final result. Having such fine granular operators can also be used to map other data flow workloads like graph processing. This is demonstrated by Spark, Weld, or the work on differential data flow for iterative computation. Until now, we have spoken a lot about how to freely combine suboperators, how much more possibilities this gives, but one might argue that having this plethora of choices now for building query plans even more than before, optimizing will be an impossible challenge. However, we think actually it's the other way around, and it gives us more structures. For example, if we start with an SQL input, we will of course use the query optimizer on relational algebra. Query nesting, join ordering is much more feasible on this level. However, when now lowering to suboperators, we have another chance to optimize the data flow, since each suboperator is a rather small logical block. Its coast model then is also an overseeable coast model, and we can optimize and combine over the operator boundaries. Finally, we of course trust in compiler for building the most performant assembly code. This layered approach we just presented is also well in line with the latest proposals from the compiler community like TVM or MLIR, which propose multiple intermediate representations for the static optimization. This structures code generations and optimizations to perform these lowerings efficiently. All these three layers, however, are still static optimizations at code generation time. Having the suboperators now and the possibility to use disaggregated resources, we can also employ techniques from microadaptivity at runtime. Thus, we compile different variants of the query plan to choose the best one at runtime and reconfigure them, which corresponds to the ideas from the work on deep query optimization. Now to conclude, suboperators offer a multitude of benefits. They don't really enforce relational algebra anymore as an intermediate step, which allows us to reuse the existing step from a database system and overcome the limits of SQL-like query processing without reinventing the wheel. And they are mostly even present in our current database management system, though not exposed. Also, they have a notion on how the data flows and when it has to be materialized, which lets us disaggregate the compute resources and makes it future-proof. By storing properties like order or minimum and maximum values in the materialized buffers, we can also help to pick the best implementation. Since each of the suboperators is fine granular, providing implementations and coast models for different hardware targets is feasible. This allows us to adopt modern hardware fast and conveniently. It is also the granularity where we can upload code to FPGAs or cross-grained reconfigurable architectures. These are faster to program than FPGAs and offer building blocks for mapping data flows into logic. It might also give us a chance to influence future hardware developments. And now finally, we can optimize the suboperator data flow, which adds a new level for the optimizer. This also provides an optimizer for every domain-specific language that maps to suboperators. So we can also offer an optimizer, for example, for graph or machine learning workloads. Thanks for your attention, and I'm happy to take suggestions or queries via email.